lot of putting together over here, and thanks for also involving ICTS in it. The talk will be mainly devoted to explaining what the title means. This thing called the highest spin square, so don't let that intimidate you. So this is based on some work I've done and to appear with Matthias Gabriel. So the plan of the talk is the following. So first I'll sort of motivate the context for this investigation, and it will be so I'll try to explain this in the first few slides about how it's potentially very useful to try to search for a maximally unbroken phase of string theory where the symmetries are sort of maximally unbroken. So with that motivation, I'll go to a specific example where we will see a large unbroken symmetry, and the rest of the talk will be in trying to characterize that symmetry, some of the consequences of that symmetry. This will be in the context of a particular description of a string background in terms of a two-dimensional CFT known as the symmetric product CFT. I'll briefly, I mean, this is familiar to most people in string theory, but I will put together some basic facts about the symmetric product in formal field theory, and in particular, we will be looking at the sort of the single particle generators of all the conserved currents, which will determine the symmetry of this background. To uncover the structure of the symmetry, we'll sort of focus on a sort of a simpler version, sort of a pared down version of this, which will be not really dual to any bona fide string background, but it will just involve a single boson symmetric product. It will capture algebraically many of the features of the symmetric product CFD, of the actual CFD. So in this context, I think we'll be able to exhibit this higher spin square structure most minimally, and I think it's a very interesting mathematical structure. This is an unusual, unfamiliar, and sort of, to me, unusual mathematical structure, which I haven't quite been able to place. I've talked to some people, including the audience, about its context, but I haven't really managed to locate it in its best sort of mathematical home. In any case, this square, I think there's a finite dimensional analog of it in terms of the Clifford algebra, which I'll explain to you. But more than its mathematical structure, I mean, I think the mathematical structure is interesting because it gives you a potential handle to exploiting this symmetry for the string theory. For instance, we look at some of its simplest representations, which will be part of the matter sector of this theory, and similarly the twisted circle. So one of the themes which will come out in this, I hope, will be that in some sense the string theory can be understood as a very sort of a souped up, very much more complex version of the Vassiliev higher spin theory. Many of its structures are sort of very analogous, except the symmetry is much bigger, and therefore its representations are much bigger, and so on. So perhaps that since we have some understanding of the Vassiliev theory, perhaps this might be a useful way to characterize the full string theory and its unbroken symmetries. So this I'll finally end with some outlook. Okay, so that was sort of a little bit elaborate plan. So let me say a few words of motivation. So I think anyone who has worked on string theory finds its structure, finds it very fascinating, because in some sense it's very rigid. You cannot tinker with it very much, and you would spoil all its good features if you try to do something stupid, and if you change things a little bit. But this rigidity is not something that is manifest in the formulation. It's just that there are a certain set of rules that you follow. I mean, the rules of string perturbation theory in terms of Riemann surfaces and so on. You try to move those rules around a little. You don't get anything meaningful. So it's certainly very rigid that way, but it's not manifestly so from the space-time point of view, and especially it's not clear what is the sort of underlying principle that determines this structure, and why is it so unique. And there has been an old speculation that this is perhaps due to a sort of a very large invariance of the theory, space-time invariance, which is mostly unmanifest. So, for instance, in flat space, only Yang-Mills gauge symmetries and diffeomorphisms are obvious from a low energy point of view, at least when you write. But even from the rules of string perturbation theory, it's clear that these are exact symmetries or invariances, but that's about it. But these people in the late 80s, in flat space, they tried to uncover hints of this larger invariance by looking at a particular limit where you take this dimensionless combination, which is the ratio of energies to the string tension. So alpha prime is sort of 1 over the string tension. So this is a dimensionless quantity, and you can take this limit going to infinity, so you can view this either as a sort of high energy limit, so E is the characteristic energy of the states that you are considering. So if you look at this high energy limit, you find some simplification amongst in the amplitudes between different string scattering, between the string scattering amplitudes involving different string levels, something that's not obvious when you just look at the individual amplitudes. In fact, the individual amplitudes for some highly excited state are very difficult to compute, but if you look in this limit, they are sort of all more or less proportional to the same thing. So there's a sort of simplification in this limit, which gives you linear relations between amplitudes. And whenever you have linear relations between various amplitudes, that's a signature that there is some kind of relation, a symmetry relation, or a Ward identity in the technical language relating these amplitudes. So there seem to be these sort of hints.
There are these gauge, these sort of the BRST exact states at every level in string theory,
right,
that appear to be like gauge invariants.
Right. So that's another hint, in fact. Yeah.
I was just wondering whether you could produce some sort of gauge group that would give you these relations. I mean, has that been understood in any way?
Yeah, I think that was sort of vaguely the thought at that time, that in some kind of string field theory there is a QBRST symmetry of the huge string field, so this big BRST symmetry transformation is some kind of large gauge group, but I don't think anyone could use that in any useful way to.
For instance, these linear relations that you're talking about have not been derived from.
No. Because this is sort of, it's very kinematical. Also, it's in this limit. It was obtained by looking at the saddle points of the string amplitudes, which you get from particular points in the moduli space. So what basically happens is that in this kinematical limit, if you try to evaluate the string integrals, they sort of get contributions from very, you can do it in a sort of a saddle point way, and you find that they get contributions from basically certain set of some loci in the moduli space of Riemann surfaces, and then when you evaluate it on those saddle points, all the amplitudes are essentially sort of roughly proportional to each other. So there's a sort of a, so that kind of simplification I don't think one has seen through any, these relations one hasn't derived from it.
So Rajesh, you're talking about the Grossman kind of limit.
Right.
So how did that relate to, how did that lead to relations between amplitudes of different strings?
Yeah, so Gross-Mendel first did the saddle point calculation, then Gross had a follow-up paper in which he showed that if you evaluate, basically it's very simple because the prefactors in these string amplitudes don't really care about the saddle point. The saddle point is from the e to the I k dot x or vertex operators. So then you evaluate the amplitudes on those saddle points, you get some relations between different ones.
There's some universality which is to loops, you mean? That's what you
Sorry?
mean?
Even this tree-level scattering amplitudes on the sphere, if you take, you get some saddle point. That saddle point is just determined by the external momenta. And then you evaluate it on that saddle point. The external prefactors just contribute some sort of very some kinematic piece. So so the bulk of the thing is essentially this e to the I ki dot kj type of thing. So you get a set of linear relations. So that's a very short paper, of course. You can see what those linear relations mean. No one has really understand, and one hope is to eventually maybe try to connect up this to what I'm going to say in the rest of the talk. But in any case, so all this was in flat space, and in flat space, in a sense, it's a little unsatisfactory, the whole thing, because it's not this tensionless limit. Because you can view this as a high energy limit, or equivalently, the tension is going to zero. So firstly, this suggests that this tensionless limit is maybe a good place to look for unbroken symmetry. In a way, the tension is like a mass scale, which in the theory, and it's sort of perhaps that's dynamically generated. But in flat space, since there's no other dimension full parameter in the theory in the background, it's not very clear how to take this limit uniformly in the theory, except on some kinematic regime or in particular states. So that sense, flat space. So if you naively try to take a tensionless limit, you get a very singular theory, and it's not clear what to do with it. But then, of course, in the 80s and so on, people basically knew flat space and a few related backgrounds. But nowadays we know many more. We understand larger class of backgrounds, and in particular about anti-de Sitter backgrounds. So in a way, it is a little counterintuitive that maybe flat space is perhaps not the place to see this unbroken symmetry. But in any case, you could, since we have these theories on ADS, we could try to look at the tensionless limit there. And in fact, there are many cases that we now understand fairly well. We have string theory on ADS 5 times S5, we have string theory on ADS 4 times CP3 or whatever, and ADS 3 times various spheres and so on. So we have a variety of these backgrounds in which we know a dual conformal field theory with a good deal of reliability, and the dictionary there tells us that now you do have a dimension full parameter. That was one good thing of going to ADS. So there's the curvature scale of ADS, and so that divided by alpha prime is a dimensionless quantity. And the ADS CFT dictionary tells you that this is typically some positive power of the coupling constant of the CFT. So it's lambda to the 1/4 or lambda to the half in the case of ADS5 and S5, where lambda is the coupling of the CFT, the Toft coupling or whatever. So this dictionary tells you that taking this ratio to 0 is equivalent to taking the theory CFT to its free limit. And this was the observation of Unbroken, later written, that the tensionless limit is a very nice point it's a very special point from the dual CFT side. There are free CFTs. Free in the sense that they are Yang-Mills theories at zero couplings, which are, so they're not totally free, but they have the Gauss law constraint, but they are essentially the lambda goes to zero limit of the interacting theory. So the dual CFTs we understand. So even if we don't understand the string theory directly, the string theory on anti-de Sitter space is something we don't yet have direct analytic control over. But we understand the free CFTs. If there's any CFT we understand, it's the free CFTs, so there we know that there's a tower. This free Yang-Mills theory, the spectrum is something we can explicitly study, and one knows that there's a tower of higher spin conserved currents, which are bilinears in the field, and so which are basically like phi to the S phi, something like this, various powers of various derivatives acting on both sides. And so these currents are higher rank tensors, which are conserved at the free point, but not otherwise. At least for spin greater than 2, they are not otherwise conserved. And the ADS CFT dictionary tells you that these are dual to some gauge field or rank as gauge field. And this being conserved means that this has a sort of gauge invariance. And there is indeed a theory of these of interacting higher spin gauge fields with spin S greater than 2. So here you typically have, let's say, spin 1, spin 2, and so on, a whole infinite tower. So this is on the CFT, on the gauge theory, on the anti-de Sitter space-time. There's indeed a theory of all these interacting gauge fields, which is the Vassiliev theory, as probably many of you have heard. This of course is a complex theory because it has not just the diffeomorphism invariance or some kind of gauge abelian or non-abelian vector gauge invariance, but it has gauge invariances associated with each of these, and they are non-linearly interacting with each other. So it's very difficult. In fact, was not even clear that there is a consistent interacting theory of all these fields. And in a way, you can say the Vassiliev theory is a prime archetype of a structure which was quite determined by this underlying gauge invariance, namely of all these. So at the linearized level, there is some sort of gauge invariance like this, but then the challenge was to sort of close this nonlinear algebra of all these fields and write down at least a set of equations. And Vassiliev, after sort of heroic 15 years, managed to accomplish that. And there are now many checks of that. So it seems like it's an established theory at the classical level, which is determined quite uniquely by gauge invariance, by the underlying gauge invariance. In fact, in a way more so than even say Einstein's theory, because Einstein's theory at two derivative level is completely fixed by gauge invariance. But if you allow yourself higher derivative corrections, and which indeed are there, and there is of course zillions of terms you can write down consistent with diffeomorphism invariance. But in the Vasiliev theory, there seems to be just a few parameter freedom, very little which you can really tinker around with. So that's quite encouraging, because that's the sort of thing you would expect. That's what we were started off by looking for in string theory.
Question about that. If you do loops in Vasiliev theory, you generate some effective action that presumably continues to have the gauge invariance.
Well, I mean, if the theory is not sick in at least directly trying to quantize it, but yeah, maybe in some hand-waving way, yeah.
So there must be ways of generalizing Vasiliev's theory with some horribly non-local way.
Yeah, but I think that's the thing. I think it's not very clear that with its matter content as it stands, it is a consistent quantum theory. Whether you can
at least
generate a sort of a
the theory that comes from EVJ theory should be consistent.
But that would be a string theory in some sense. So it will have so it has this whole non-abelian this thing. And similarly here also we'll see that the canonical Vasiliev theory needs to be coupled to sort of additional representations to make it a sort of a consistent theory. So at loop level, I think unitarity or whatever will force you to introduce additional fields to make the theory sort of better defined. So the Vasiliev theory is an example, as I said, of a structure which is fixed by, determined largely by the gauge invariance. So you can ask, is that the maximal set of unbroken symmetries, at least amongst these ATS vacua? Because this is one tower over here, and this free Youngman's theory that you want to find. So the free CFTs we understand, and in fact you can sort of sit and enumerate what are the conserved currents which are dual to the gauge fields. What are the conserved currents, and basically in generic ADS vacua, these are the only conserved currents. But in ADS3, there's a sort of an exception to the situation, and that's one of the things I want to sort of take away. That ADS3 is special in that there's a much larger set of conserved currents in this theory. In fact, exponentially larger unbroken symmetry algebra, and that is this higher spin square. This exponentially larger set of currents. So now you have currents which are not just bilinears, as we'll discuss, and it's easy to see they are exponentially larger. The Vasiliev currents are there as a small subsector, and in fact they help to organize this whole bigger symmetry algebra in a very definite way. And so that's good, because it's already much larger, because this is, after all, this is of course much bigger than the Yang-Mills and diffeomorphism invariance which we have in flat space, but it is still a very small fraction of the string states. So if you want to have linear relations between arbitrary levels at string theory, this is not going to do the job. But you need something much larger. This is exponentially larger. You'll see that it is sort of like a Cardi growth of states. So it may, it's still not Hagedorn like exponential, but it is sort of e to the square. So basically, so here the number of fields at spin s, gauge fields at spin s in this particular case, this is independent of s. It's finite number, but independent of s in this Vasiliev case. But in this particular ADS3 background, we'll see that the number goes like exponentially as e to the square root s, which is still much less than e to the s, which is sort of what you would imagine is the Hagedorn growth, but at least it's much bigger than the independent set of independent of s feature. Okay, so you might hope that these can constrain the theory much better. So okay, so I spent quite a lot of time on the introduction. Let me just tell you sort of before, in case you get lost in things, let me just tell you what the
the back.
So let me just tell you what the punchline is. That if you look at a particular background involving ADS3, as I said, times the sphere and T4, and the unbroken symmetry algebra can be organized in terms of the Vassiliev higher spin symmetry into the sort of this higher spin square. So the symmetry is exponentially larger, as I said, but it's effectively generated by two higher spin symmetries, or W infinity symmetries as it is called. And when I say effectively generated, what I mean is that all the commutators of the symmetry algebra are expressed in terms of these two higher spin commutators. So this is the mathematical structure which I would like to understand a little better. At least you normally hear of direct products of tensor product of two algebra, or two symmetries, in which, of course, the commutators or the Lie algebra of the combined thing is determined by each individual one. But there, the rank of the combined thing is the product of the individual ranks. So if you had something which was, say, linear, you would get something at most quadratic. So it would not generate something exponentially larger in rank, whereas here you have a structure which sort of generates effectively this exponentially larger algebra is still determined by the commutators of by the Lie algebra of just two underlying higher spin symmetries. So it's
determined in a simple practical way.
I mean, there's an algorithm you can give for given, say, any 2 points on this. There's a finite algorithm. Yeah, algorithm you can, which I will explain. It's a bit so okay. So let me now explain what this symmetric product CFD is. By the way, about this previous higher spin square, I mean, I'll concentrate mostly on the...
Can we focus on the transparency?
Sorry.
Sorry, Justin.
So I'll focus mostly on the symmetries, which are, of course, the conserved currents of this CFD. But there are also the matter sector of this, and I'll just say a couple of they'll have a couple of transparencies on this at the end, and they will also be in some very canonical representations of this in this larger square. So everything, I think, can be organized in terms of the symmetry algebra and some of its sort of small representations, and in a way which is very analogous to actually the examples of vector holography for higher spin theories. But for those who are more familiar with that, I'll say something at the end.
The rank of each group is infinite.
Yeah, so it's a better characterization is how many states are there at any given spin, let's say. That's one way to sort of keep it finite and then see. So as I said, these are independent of the spin, whereas this one will grow exponentially with the spin. So you can see it's a much bigger infinity than the previous one.
So you got this algebra which is determined completely by two much smaller algebras.
Yeah, exactly. So supposing you had SUN times SUM, the rank of the two things would be n times m, but and the commutators, of course, are determined by this. But this is somehow some other product of SUN times SUM. I mean, roughly speaking, which has ranks something like e to the square root n. So Yeah. So that's why I find it quite unusual. And is there some natural way, at least for these algebras, to generate something much, much bigger from just the commutators?
And it's very particular to these two algebras. It's not a general algorithm saying given any two algebras.
I don't know. I think this Clifford algebra suggests that this is part of this is not the only example of such a thing, but there's a family of such things, so that's why it'd be nice probably to understand it in its mathematical home, so to say. But anyway, so the string theory on this symmetric on this background is believed to be dual to a CFT. Which is a deformation of a free CFT, a two-dimensional CFT, which is what is called an orbifold CFT. So it's a free CFT in which you have, let's say, n copies of torus, T4, and you orbifold by the symmetric group action on those n copies. So this is something that a lot is known about such theories. They are free theories, so you can say a lot of things explicitly about them. And in fact, mathematically, these things have appeared also, I think, in studying the moduli spaces of instantons in Yang-Mills theory. And I think the work of Nakajima and so in sort of these resolutions of the mathematically, I think it's called the Hilbert scheme. But in any case, the partition function. So if you know the theory on T4, that determines explicitly the partition function of this much bigger CFT. So if you know the single particle sort of just the Q expansion of this original CFT, let's say X is T4. This is true for a general X. So supposing I know the partition function on X, then the generating function of the partition function on the symmetric products is given in a very simple form in terms of these coefficients of the. So Q is the usual e to the 2 pi I tau, and its complex conjugate. So the generating function is just given in this very nice product form, which exponentiates these coefficients. So this is essentially, from a physicist language, it is a formula for taking multi-particles, because this is sort of like the Bose Fermi exponentiation from single particle states to multi-particle states. And in particular, this is for the full partition function. That means all the states of the theory, but you can apply it to the chiral sector. The chiral sector is the piece which consists of only, say, the left movers or the right movers. So that's the sector where, say, h bar is 0, for instance. So that's the subset of these states, which correspond to the chiral sector is something you can also read off from this. So you...
sorry, I probably be stupid, but I've not seen the twisted sectors in this formula.
Sorry, yeah. So this is in the... Sorry, I should have said this is for the untwisted sector. This is for the untwisted sector. So we will focus on the untwisted sector for the moment, and we'll deal with the twisted sectors separately. So the untwisted sector is basically the sector which is just the orbifold invariant states invariant under this, but there are also the states which are sort of twisted up to elements in Sn. So you can sort of you can take things which are in the CFT twisted sector, which will not immediately consider. But in particular, if you want to read off the chiral sector, the conserved currents, those are all in the untwisted sector, you can read off the conserved currents from this partition function. They are in sort of one-to-one association with the, at large n, they are in one-to-one association with the chiral algebra of X itself. So this, if you look at the chiral part of this, namely the part which is, say, independent of which has h bar equal to 0, that's of course huge. But a lot of those are multi-particle states, because products at large n, products of currents will also be, so you can take the square of the stress tensor, that's also a sort of a conserved current, that's also holomorphic. But you don't want to look at the states in the dual, which are dual to the gauge fields are the ones which correspond to the single particle conserved currents. So you're interested in identifying which are the single particle conserved currents amongst these states. What I claim is that you can, there's a very simple association of the single particle conserved currents from the fact that basically this is a multi-particling formula. So what you do is basically consider, if I know the currents of X, the original theory, in this case, say the T4 theory, if I know all the conserved currents of X, the single particle conserved currents of X to the n mod Sn are just in correspondence to, given any current in X, I just consider the symmetric combination of the over the n copies, this will be a single particle current, conserved current of the symmetric product. So basically, given any element of the chiral algebra, you can find of X, you can find the single particle conserved current of this symmetric product.
Rajesh, you're going to explain this step?
Yeah, a little bit, in the sense that, so for instance, on T4 to the n mod Sn, the claim is therefore that there's a one-to-one correspondence with the chiral algebra of 4 free bosons and 4 free fermions. So of course it is clear that each of these are conserved currents, and they are single particle because they are sort of single cycle. They're the sum over 1 to n, and they're all independent at large n, because unlike, so if if I just were to look at the currents on the T4 theory, something like del phi to the 4th would not be an independent generator of del phi square. But at large n, del phi, summation 1 to n del phi to the 4 is independent generator corresponding to summation 1 to n del phi square. It's not, they're not, one is not roughly the square of the other. So you can, so each of these become independent generators, and you can see this, of course, explicitly from the counting also, that all the single cycle states are, you can construct all these single cycle states from the original theory, and they're all independent generators.
That's it. And even if one was roughly the square of the other, there would be independent generators in the Lie algebra.
Well, they wouldn't be sort of, they're not, they wouldn't be single particle states. I mean, yeah, in a single thing, we wouldn't think of them as single particle states.
But just, if you just took the free boson, just one free boson, there is a sense in which every holomorphic current is a independent generator.
Right, from an algebraic point of view. But from our point of view, we are interested in this thing, yeah.
Just since we're mathematical purists.
So in the T4 theory, the chiral algebra, the generating function for the chiral algebra is just those of 4 free bosons, which is this denominator, and 4 free fermions, which weighted with some chemical potential. So those are the things in the numerator. So the claim is that the number of currents at any given spin in this ADS3 theory is just given. It can be read off from this generating function. These will give you the single particle currents of the and therefore the massless gauge fields of the dual ADS3. And this exhibits the first statement that I made earlier, because this has a Hardy-Ramanujan type of exponential growth, because these are basically partition functions, and so it has a sort of a Hardy-like growth or Hardy-Ramanujan type of growth. And so the number of states at any given Q level, Q to the S, will go like e to the square root S with some coefficients. And so that's the first statement that I had made earlier, that this has an exponentially growing set of currents.
Where does this partition?
Yeah, so it's basically the ways of, in physics terminology, it is the partition function of 4 free bosons and 4 free fermions. 4 free bosons because boson states can be all occupied independently, so it's basically like a regular partition function. The states are moded by some integers, and it's the number of states you can have is counted. For a single boson, the partition function is precisely product 1 over 1 minus q to the n. So for 4 free bosons, you have a factor of 4. And for fermions, there's the Fermi, the Pauli principle. So they come in the numerator. You can't have more than one mode occupied. So their generating function, and they're half integer moded. So their generating function is in the numerator, and this is some grading of the so this the generating function of all the states for the 4 free bosons and 4 free fermions, and the chiral sector of it. So you can, it's maybe later I'll tell you what the enumeration. I think I'll have it shortly. Okay, any other questions? So fine. So this is the generating function, and this is something you could have said 20 years ago. So this is the generating function of all these single particle states. But the whole idea is to usefully try to organize these stringy symmetries through something maybe which we understand a little better from a space-time point of view, and try to see whether that organizing principle can shed some light. So that's the whole point of the exercise, is to organize these states in some nice way, and that's what this higher spin square is supposed to do.
And sorry, if we were not interested just in the currents for all particles, the Hagedorn growth would come once we looked at the
twisted states. Okay, so you could look at this chiral partition function and try to look at its algebra, but in a way, to see the bare bones, as I said, we can look at a pared down version of this, in which we look at just a single real boson. I think that captures essentially the guts of this thing, and it doesn't have all these additional fermions and so on floating around, and 4 multiplicities of 4 and so on. So a lot of that structure is anyway fixed by n equal to 4 supersymmetry. So much of what I'll have to say has no relation to supersymmetry at all. So supersymmetry is a little irrelevant to the whole thing. So it's just ornamentation on it. So by focusing on a single boson, you can see the structure most simply, because if you were to do the analogous statements that I made, if you now consider the symmetric product of a single boson, the chiral algebra, the single particle generators would be in correspondence with the chiral algebra of a single boson. And as I said, the chiral algebra of a single boson is just the usual partition function generator, and this number. So what are all these things? They are basically built from various monomials. So you have a single boson, and you consider arbitrary many holomorphic derivatives on it, and monomials to various powers. That's what this generating function essentially counts. So you can so all of these are so the single particle ones will be symmetrized combinations of these. So in particular, there's a subset of these monomials which are the ones which are bilinears in the current, sort of like what I wrote over here, with some coefficients. This subset is the subset that corresponds to the Vasiliev type fields. They are, or in the CFT language, they are the generators of the so-called W infinity symmetry algebra. In this particular case, for a free boson, the W infinity symmetry algebras are labeled by a parameter. The free boson corresponds to when that parameter takes the value 1. But anyway, never mind that. That's just to fit in the algebra of this into a broader context. You can just work out all the commutators of these. They are well known. They are explicitly known in terms of factorials and so on. So you can. So this W infinity. It's a linear algebra, by the way. I should say it's a Lie algebra. Unlike you might have heard maybe that the W algebras are sort of not proper Lie algebras because you have quadratic terms on the right hand side. But these ones for free boson, they are just linear Lie algebras.
So that's a special thing about lambda equals 1.
1 and lambda equals 0, which is free fermions. So those are 2 points where you can, by appropriate field redefinition, write it in a linear way. Which, of course, the theory of free bosons and fermions tells you that it must be like that. But, so and those are the two that will appear over here. So these high spin symmetries that appear over here are genuinely algebra symmetries. Okay, so you have, but this is a small subset. These are just bilinear fields, and there are, for any given spin S, there's just basically, in this particular case, just one of them. There's a single real boson. There's just one. That's why I said it was independent of S. Whereas so when you expand this out, there's a partition function of S times Q to the S in this expansion. Out of that partition function, there's just one which corresponds to the Vasiliev-like W infinity symmetry algebras. All the remaining exponentially big number of them are generated by other higher monomials. So that's the structure of this algebra. But there's once you sort of try to look at this algebra through the lens of this higher spin symmetry, there's a very nice way you can characterize all the other monomials in terms of this algebra. These other monomials, in fact, transform in very specific representations of this W infinity algebra. Namely, in fact, you can organize all these monomials in a very simple way. You just look at how many powers of the fields appear. So the bilinear ones were the ones with, you have two bosons appearing, so that is this second column. You see there's sort of del to the L phi, del to the K phi. But you have a single monomial with just arbitrary derivatives of phi, and then you have ones with cubic in the fields phi, but arbitrarily many derivatives, similarly quartic in the fields, arbitrarily many derivatives. You have all these towers, right? That's a simple way to stratify all these, to organize all these monomials. And what you find is that each of these, in fact, is in a very specific representation of that W infinity algebra. The W infinity algebra representations are labeled by some Lincoln labels, and these correspond to that language. A little counterintuitively, they correspond to antisymmetric representations. You might have thought they correspond to symmetric representations, but there's sort of a split anyway. So they correspond to some, basically the nth, the set of fields with n, the column with n fields phi transforms in the nth antisymmetric representation. So that's what. So you have an infinite set of these columns, and so you can divide up all the generators of this bigger algebra in terms of these columns. And in fact, and each of these in some particular representation. And in fact, this decomposition actually corresponds to a nice identity for the partition function, which can be written like this. It's some identity going back to Gauss But it's not very difficult to prove. In fact, it looks a little bit formidable, but it's actually very easy to show. But the significance of this identity is that these are the characters of each of these representations. So this whole generating function of the chiral algebra can be written in a character decomposition in terms of this higher spin symmetry, and each of these are the characters of these representations. So you can look, people have studied W infinity representations, you can go and look at the character, and the character is this, so you sum up all these and you get this, so which is just a statement that this is a full decomposition of this chiral algebra. Okay, so this is what we call a vertical decomposition, and this algebra, W infinity algebra, which is these bilinears, I will call this the vertical W infinity algebra. Yeah.
What does the single field things represent?
What does it represent? It's like a no. What do you mean? It's basically they're trivial because it's basically the U1 current del phi and all its descendants. So yeah, it's a little bit of a trivial representation, but it's
by this phi i's, you mean just phi here or not?
Yeah. So really, the I is for the label. There should be a sum over I equal to 1 to n. So the I is really this I label shouldn't have been there. The I is the label of the copies. You can drop the I if you for the full thing. It's the copy labels. Yeah, for the n copies of the symmetric product. But if you wish, you can forget about the I's. There's a one-to-one correspondence, like I said. So
the charges corresponding to these currents are just integral over z.
Over z of
the currents. So the charges are not dimensional; they have some dimension.
Dimension meaning
I
mean, like L0 is so these are the L0 values, but you can write W0, all those other values. Also. So the L0 is of course the stress tensor, the current, which dimension?
If you have a 1-0 operator and you integrate it, you get something dimensionless and conserved.
Right.
So these things will not be conserved in that sense.
These will commute with L0. L0 with there's an infinite number of things, infinite number of mutually commuting charges you can find. Is that what you?
I was just looking at the weight of these. Sorry, stupid.
Yeah, the weight is like you integrate
just weight of the current
minus 1.
And the weight of the current can be arbitrary.
Yeah, exactly.
So it's not zero weight.
It's not zero weight.
Okay. And to find the commutation relation between the charges, we just take the pole and the
L0, W0, the zero mode of the currents, and then you
fuse them, take the pole, and then use it.
Right. And that's what determines the full W infinity algebra anyway. So this is one decomposition. So you could say, okay, so the structure of this larger algebra of this so all these are generators, and these are different representations. So by the way, by these columns mean that these are descendants. So you can imagine a highest weight vector in each of these columns, and then the rest are acted upon by the W infinity generators. So there's an infinite tower. In fact, it's a little misleading visually because it's really like a pyramid, so it'll keep growing. But anyway, and these are highest weight states and descendants.
That was a stupid question. Yeah. Suppose you take one of the bilinears and you've got something with 10 phi's. Mm-hmm. So one thing you can do is take the OP where you fuse one of these guys with the other, and that will once again give you something with 10 phi's. Mm-hmm. But what if you fuse both of them? This guy and this guy,
you will get something lower. You'll get lower. So the generators, it has a triangular structure. So you'll get generators of spin S plus S prime, and S plus S prime minus 2, S plus S prime minus 4, and so on. In general, if I fuse S and S prime.
But I've shown the number of phi's.
Right, so that's the same. Okay.
There will be phi's in a representation.
Yeah, at the top of this thing, it will be. So you have to so you have so each represent to write things which are sort of primaries, you have to sort of
I see all of these guys are the same. All these funny guys are the same.
I should say one thing, yes, given that Shiraz was asking also. So this enables you to take commutators between something here and let's say something here. In the sense that you know those commutators in terms of the W infinity structure constants of the Lie algebra. But between two arbitrary columns, of course, you can take the free field in this thing, but that's whatever it is. It's not obvious that it has anything in terms of the W infinity algebra. To see that structure, you can actually slice up these generators in a different way. There's an alternative way of slicing the generators in which you sort of do a horizontal slicing. What do I mean by that? You first take the terms, if you wish, the top row of each of these columns. The top row is the one in which you have just the least number of derivatives. So you just take in each column just del phi to the number of the power, which is n in the case of the nth column. So that's what written over here, del phi to the n. So this row is all the just various powers of del phi, and that's the top row. The next row you add more powers of del phi, and so on. There's a way of slicing it in this way. But the interesting thing is that this top row involving all these del phi to the m by a fermionization, so in 2 dimensions, there's the Bose-Fermi equivalence, and you can write these powers of phi can be written simply as bilinears of fermions. So they can be written basically in terms of some size, but with just 2 size and arbitrary many derivatives on the size, on the fermion fields. So this top row generates a W infinity algebra, a different one, which is the one which you get from these generators. So this is, if you wish, some W tilde S is like this, whereas the original WS is something like this. So you have a new set of generators over here, which are basically bilinears of these fermions. They form a closed algebra. That's another W infinity algebra, strictly what is called W1 plus infinity. That's because they have this spin 1 current as well, and it's at this parameter lambda equal to 0. So it's a different higher spin algebra which these form, and that the commutation relations of these as well explicitly, like you do for the free boson. Yes.
I thought that under fermionization, this del phi would go to something like psi. So
del phi will go to psi, exactly. That is the lowest member of this psi bar psi. And del phi square is the stress tensor that will go to psi bar del psi. Right? I mean, del phi square is the stress tensor, and that will go to psi bar del psi. And then higher powers similarly will have. You'll have to actually subtract out some lower order pieces. Del phi to the 4th will be psi bar. Del phi cubed will be the spin 3 current, and so on.
So Taylor expansion of the e to the phi keeping it.
Yeah, exactly. So this thing also generates a higher spin symmetry. And the nice thing is all the rest of the way you can slice it, these are also, the other rows are in different representations of this horizontal W infinity algebra. So each of these is not just some, so this is not just some sort of nice feature. But this is a useful way to organize the rest of the generators in terms of different representations now of this algebra. And in fact, you can write down what the representation is. These are now some kind of symmetric representations in terms of the labels. So if you look at the characters of these representations, they take this particular form, the mth representation. So the m labels the rows now. And so the rows, and each of those rows are some representation. This representation, you look at their characters, it's something like this. And you sum up all of them, that's again this thing. This is another identity also due to Gauss. I think, anyway. It's another identity for the Partition function, and it's true. And it's also not very difficult to verify, but it's a different way of slicing the generators of the single free boson. And having done this for the free boson, I guess all of you can imagine that for free bosons and so on, the fermions will be just some souped up version of this. But this captures the basic bosonic structure that underlies this. So
sorry, one thing. So the null states don't appear in either way of organizing
which
these.
null states? I mean, there are, of course, yeah.
So you're constructing representations of W.
Infinity, yeah. Right.
So
there are, each of these have lots of null states. Each of these representations, in fact, have lots of null states because, I mean, it's like the vacuum representation is annihilated by W minus 1. And so similarly, there are many null states. So this character is the full character, taking into account all the null states. Yeah.
But the null states, the way they appear in the vertical way of looking at it and the horizontal way of looking at it would be very different. I mean,
right? They are exactly. But
this is with all that stuff.
Yeah, it includes all that. Yeah, but the null states are just those of currents. I mean, they're just the usual conservation.
They're just zero in the
field.
Yeah,
exactly. Yes. So having this decomposition, we can therefore view the whole set of generators in this language of a square. You can slice it vertically, you can slice it horizontally, so anything will lie on what I showed you by those character expansions is that any particular generator lies in one particular horizontal column and one particular vertical column. Every generator is somewhere in this table. And so some particular M, which labels one row, or some particular N, which labels one column. So every generator is somewhere in this square, and it's labeled by two coordinates, if you wish, N and M. In the square. And each of these are, so the descendants act, the horizontal W infinity algebra descendants act this way, and the vertical one descendants act this way. So now you can, suppose I want to take the commutator between an element here and let me not take on the second, between an arbitrary element here and an arbitrary element here. So you can, in fact, there's a nice consistency requirement also, which I don't know. You can do two things in trying to take this commutator. So this is a descendant, you can sort of go to the top, right? This is a vertical, this is a descendant by the vertical W infinity, it's a descendant. So you might as well go to the top over here. Similarly, this one is a descendant of something over here. You might as well go to the top of that column. Then you take the commutators here. Those are given by W infinity commutators. You know those. So that's one way of computing this. But you could have alternately gone this way and gone to this column and taken gone here. And similarly, this one you could have gone here and then taken the vertical W infinity commutator. So in fact, there's a consistency requirement also that these two algebras satisfy. There's some in this thing that some Jacobi identity type of thing that whichever way you do it, it should form a closed algebra. So as I said, it's these two algebras, their commutators completely determine their structure constants completely determine the structure constants of this bigger algebra. And you don't need any additional information. And yet it's exponentially larger in rank. So what that means, it's an interesting way in which the representations of the algebra themselves become part of the Lie algebra. And so, I don't know. There must be some nice way to say this, but I don't know. So so just to try to make get a analogy. Actually, it's this finite dimensional analogy is not a very precise analogy, but it will capture some aspects of it. As I said, it's not a tensor product of the underlying higher spin algebras in any sense. And it's exponentially larger in size than either the horizontal or the vertical algebra. Sorry, I'm just taking 5 minutes. So I'll illustrate this in a simple example, which you don't need to know about W infinities or anything. You just need to know. We don't have any school students here, but I think the undergraduates here will at least appreciate Clifford algebra. So if you so the Clifford algebra, let's say in some the Euclidean dimensions, is like this, and the bilinears. And that's why you introduce the Clifford algebra, because these are the Lorentz generators or the rotation generators of the SO2D. So if I am in 2D dimension, there are 2D of these gamma matrices, and these antisymmetric bilinears are generators of SO2D in the spinorial representation. So the other products, you can consider all the antisymmetric powers. They transform in the nth antisymmetric representation of SO2D. So I can again label, I can think of a vertical slicing in which I have gamma I1, gamma I, let's say the first column is just gamma I, second column is gamma I, gamma J, and so on. The nth column has gamma I1 to gamma IN. Antisymmetrized, and of course this is finite dimensional, so there are just 2D columns. The maximal number is 2D, so you can organize these labels. Hello?
Yeah, we are good.
Yes. Yeah. So I was just saying about the Clifford algebra, and I'm just indicating that you can consider the nth antisymmetric representations of SO2D as a column in which you take some highest weight state of the SO2D, and then SO2D acts vertically, and you have all the descendants. So you have columns like these. So that's fine. So you know, because these are in the antisymmetric representation of SO2D, you know the commutators of this with these generators. It must transform in the structure constants of SO2D in the antisymmetric representation. But because of the Clifford multiplication of these gamma matrices, you can actually take the Lie algebra between arbitrary elements of these columns, not just between the nth one and the bilinear one. You can take between arbitrary columns, and in fact, we know what the whole Lie algebra is, because all these gamma matrices are all independent, as you have probably proved when you studied direct equation. These are all independent and traceless and so on. So these generate, in fact, and in 2D dimensions, the size of the gamma matrices is 2 to the d. And in fact, these generate all the independent 2 to the d traceless Hermitian matrices, so they generate SU 2 to the d. Or U 2 to the d if you add the identity. But whatever it is, it's exponentially larger than SO2D, have rank d, growing linearly with d, whereas this is exponentially growing with 2d. So it's sort of similar in spirit, in the sense that there's this column decomposition, and you can act In fact, there's a sort of a horizontal action. There's no horizontal Lie algebra as far as we could see in terms of the top entries. I mean, maybe, we couldn't at least find there's some kind of a horizontal action. You can take the kth column and the 11th column and their algebra looks a bit like these W infinity algebras in the sense that you get, lecturer said, you get K plus, you get all the gamma matrices which are the lower ones. When you sort of, it's like this fusing because the gamma matrices will annihilate each other in pairs. And you get all the lower spin ones. So it's a bit sort of like that. But so anyway, for what it's worth, I'm just throwing this out as the closest I could think of.
But it's not an example of two algebras generating.
Yeah. So if we could really find this one, that would be really along a more exact analogy. But we couldn't quite find a horizontal, smaller algebra which generates this. But yeah, I'm not 100% sure it's not there either. So in any case, that's just an aside. So how can we exploit the structure of the higher spin square? So we have this structure where you have these commutators all defined by the higher spin commutators, and higher spin theories we understand a little bit better. So we can try to view the non-chiral spectrum. I mean, so this was the chiral part of the spectrum, the one with Q bar equal to 0. So the non-chiral part of the spectrum.
Suppose you take two different choices of gamma matrices.
Different bases.
So two different bases. They will generate their own SOD, whatever.
SODs.
But if you put them together, it sounds very plausible that they generate everything.
But so if there are, so it's two different bases in which you sort of mix gamma either or the other, some exponentially whatever mix up all the gamma. So maybe there is some way in which you can do it in that way also. It would be more like maybe there's some other slicing like that.
But that transducing not exactly your...
it may be. I mean, maybe for some choice there is something
there's
something which goes like that.
Rajesh, sorry, this construction of SUN generators in terms of polynomials of n by n SU2 generators. I'm saying you can construct this SUN algebra by taking 3 SU2 n by n representation of SU2 things and take polynomials
in this thing.
So that's
sort of like it's in the similar spirit,
but of course it's not enhancing it that much.
But n is arbitrary, I guess. So you could,
Because now even among the weights there is a commutation relation just because they are matrices.
Because you choose them in a particular representation, and then I guess that's also a sort of analog. Again, it's sort of like this. There's a vertical slicing. All the representations, there's a commutator between them. The slightly trickier thing is to have something where this horizontal one also. But maybe all of these have, and there is maybe some beautified way to thinking about it. But that's a good analogy as well, I think. So in any case, so we can now try to look at the rest of the spectrum. So, for instance, the rest of the untwisted sector is given by this. If you now introduce some of the generators. So now I'm going back to the full D4 case because that's the one really of interest. So anyway, there's a generating function for the untwisted sector as well, which is essentially what I had written down earlier, the full untwisted sector, and this is the full D4 generating function. So this untwisted sector, in fact, can be written as just a multi-particle version of a single irreducible representation of this bigger square, this higher spin square. So these are just labeled some Young tableaus, so that so you can write this full partition function as the vacuum partition function that is of the chiral sector, not square. So this you should view as, if you wish, all the gravitons and other fields, massless fields, and then multi-particles of a single massive field. Or single massive representation.
And R is a representation of
all Young tableaus. All Young tableaus.
R is a representation of what algebra?
R is okay. R is in this case just labels the various multi-particles of the single. You take the two particle states. You can write in symmetric and antisymmetric representations, and then the three particle states you can similarly decompose in terms of representation. So it is just all the different multi-particles. That is just a multi-particle. It's not. It's if you wish, they are in the tensor power representations of this two various tensor powers, symmetric tensor power.
But the tensor powers as viewed as representations of what algebra?
Of this higher spin. So this minimal representation is the simplest.
Representation of this one of these.
This bigger, of this full higher spin.
The full thing, the full chiral algebra.
Yeah, the full chiral algebra. So which can be viewed as, which of course, because the higher spin algebra is a subset, you can view as in particular as a higher spin algebra. So as a representation of the higher spin algebra, in fact, it is the minimal representation of the vertical higher spin algebra. It is the representation that Vassiliev uses when he couples his matter fields. He has basically, in addition to the gauge fields, he has to have this one other matter field, which is part of this Weil multiplet or whatever. And that matter field is in a very specific representation of the higher spin algebra. And this is, if you view this from the language of the vertical higher spin algebra, this is that. This is built from that representation.
It's probably very stupid, but naively you would expect that a single representation of the full
decomposes into infinitely many representations of this. But it's a little bit counterintuitive, but that it is actually a representation of the full thing. They're both infinite dimensional representations, and this. So those of you who followed a little bit about this coset holography, namely the fact that there are two-dimensional CFT cosets which are described by Vassiliev duals, vector-like theory, not string theories. There's a sector of the cosets which behaves like multi-particles of the basic Vassiliev field, and in fact this sector behaves exactly like that. But if you look at the twisted sectors, which I haven't exhibited in any detail right now, for instance, if you look at the two-cycle twisted sector, that is, there's some new representations coming of this higher spin algebra. They are, if this was the minimally coupled representation, these are in some sense the near, in a way they are the next to minimal representations. They have slightly fewer null states than the minimal representation. At every level they have a few less null states. So there are class of these representations, and all twisted, in fact not just two-cycle, but all twisted sector representations are in these small representations which behave like the sort of the sector which was more puzzling, which contained in that case of various light states and other things. So they behave like that. So in a way, what I think one is seeing is that it's very natural to couple the Vassiliev-like theory to a much larger class of states than this. What Vassiliev had, I think Vassiliev looked at the smallest sort of set of gauge fields plus he was forced to add this matter sector most of the time because that was sort of part of his algebra. But he didn't show that that's the maximal amount of matter that you can add, that there could be matter in other representations. And in fact, I think to get a consistent sort of a string theory or modular invariant safety or something, you need to add these other sectors. And these are additional representations. And I think that what the string theory is showing you is that in consistent string theory, you need to add all these twisted sector states, and you therefore need to add all these additional minimal representations. So there's probably some larger consistent theory, which is the string theory, which is built out of some denumerable set of states representations. But all the twisted sector representations are essentially the same representation. They just differ by their conformal dimension. So as a representation, they are basically the same. So it's I think a nice picture that seems to be emerging of the matter part as well. But this is the thing we are currently fleshing out more. So in any case, let me just stop by saying, just summarizing. The stringy symmetries can be usefully viewed through this highest spin algebras in terms of this highest spin square. The entire untwisted sector is essentially one representation, which is the minimal one. The twisted sector representations, we seem to now have some reasonable understanding of them. It would be very nice to use these symmetries to see how whether the theory, when you give a wave to this two-cycle twisted sector, which is what takes you away from the free theory, whether the stringy symmetries are constrain the theory, so it's sort of Higgsing the symmetry because you're giving a wave to a charged field. It's in a very specific representation that what you understand through this is that you're breaking the highest spin symmetry in a very controlled way by giving a wave to a specific representation. There are, group theory can carry you some way towards constraining matrix elements. So that's the hope that you might be able to see this and perhaps eventually connect with this original gross mandate type idea. So I'll leave it at this stage.
Questions? Let's start with ICTS. Yeah, go ahead, Jeff.
Yes. Hi, Rajesh. Can you hear me?
Yeah, tell me.
Well, I can't hear you actually. But
hello?
Yeah, I can hear you now.
Okay. Yeah.
So I was just wondering, that you organize the two-cycle sectors. The two.
Yeah. I showed that, right? But you can do it for any n cycle.
That's what.
You have some more representations, but they're all essentially the same. It's just a twist at the lowest dimension field. The twisted sector has a given conformal dimension. There'll be that factor, but as representations in the large n limit, they're all sort of the same representations. They have the same kind of null states and so on. So that statement seems to be true for all twisted sector states.
So the partition function of the symmetric product can be written as sum of this.
In principle, I think just based on basically the minimal representation and the next to minimal one. In a sense, the minimal one is a very special case of the next to minimal one. But basically just from just these representations, so we are, of course, in the Nebo-Schwarz NSNS sector. I'm not talking of black holes and so on. So this sector, we can write the spectrum, single particle string states, we can write in terms of this representation.
Yeah.
More questions from ICTS?
Yeah. No. Is there some insight you will get? Like I think people have studied the symmetric products for the Hawking page transition. I mean, I think there are recent work. They study the growth of the symmetric products in terms of and find whether they can sort of see the Hawking page transition. Is there some insight of that using this reorganization?
Yeah, so we are not looking at these highly excited states. We are looking at single string states. I mean, maybe these are, I mean, it's all part of the free symmetric product CFT. So this organizing into single particle, multi-particle states breaks down for these highly excited states. But maybe there's still some way to talk about them, but I haven't thought seriously enough.
Okay, thanks. Yeah.
Okay, Tiaima.
So Rajesh, you mentioned something about consistency.
Yeah.
When you had
the horizontal and the vertical algebras. Yeah.
So. And then you were also talking about adding the matter sector, which is coming from the. I mean, is your that is the consistency.
Okay. Not in the algebra, but in the full theory. Yeah. The model invariance or whatever of the CFT, the reflection of that. Yeah.
Are you saying that you are somehow driven to include these guys?
From the bulk point of view, I don't see what drives us to include that. And it's only from the CFT. We are just using the fact that this is the model invariant CFT and interpreting those results from the bulk, from a higher spin point of view. It would be nice if there was some consistency requirement you can phrase in the bulk directly, which says that even though at the tree level you can write classical equations of motion with just the Vassiliev field and its minimal sector, which is what in a sense this is the untwisted sector is. Untwisted sector is like a big souped up Vassiliev theory and with a souped up matter field coupled to a matter field. It is very analogous structure, so it's just a huge Vassiliev theory. You can probably write down the Vassiliev equations for that sector also, because it's just a star product, but for this bigger algebra. In any case, so as consistent classical theory, perhaps that is okay, but something drives you to add these additional states. Modular invariance from the point of view of the dual CFT, and there must be some analogous large diffeomorphism invariance or something in the. But you should be also. From the point of view of the bulk theory, that you add these additional states. It's a bit like open-close string, I think, in a sense that in the loops of the open strings you have to add the closed strings. So maybe here this is the only way to get at the quantum level. So at the classical Vassiliev theory you won't see this, but in the torus partition function you need to add all these things together.
So there was this algebraic way of understanding modular invariance, that is to say locality of the operator product expansion of the various operators that appear in a modular invariant theory. So would that have an easier interpretation in terms of the bulk force? I'm saying that, right? I mean, modular invariance forces me to consider.
If you go around some cycle or something, that's what you're saying. I mean, if you sort of take this thing and you'll be forced to include all the modular transforms of all the states as well. I mean, how to translate that in the bulk, I don't still know. But maybe all these things, people have been trying to sort of translate the CFT.
Doesn't locality constrain the twisted sector states to say that it cannot be larger than a center? I mean, if you just stick to the untwisted sector and you work on the plane, you don't
You'll
see any
never
problem.
see it. Yeah. So classically, you'll never see it, but on the torus,
I see. Yeah, that will always form. And,
It's a consistent truncation of
Yeah.
the.
But I think what he was meaning was the OP on the torus. If you
I see,
maybe
I see.
take one operator around a cycle or something like that, then some monodromy type of.
I was thinking the cylinder.
Or cylinder, maybe.
The cylinder is
Cylinder, I don't know.
Yeah.
The torus, I think you'll need to. Maybe you take one operator around the around some cycle, another one in a complementary cycle, and some monodromy. I thought that at least I was interpreting your question.
Sorry, along the same lines. Suppose you just move to one higher dimension. There, once again, you have the minimal Vasiliev theory, but we believe that corresponds to a complete theory because it's dual to the effective vector matrix. Let's say let's say it's Wilson Fisher, the thing dual to the Wilson
Okay,
Fisher.
on the sphere, S2 times S1.
Yeah, let's say. Yes. Maybe you need to add the extra states of
The Chern-Simons.
the Chern-Simons, pure Chern-Simons. It's finite dimension, finite number of perturbation states. But just because the vector theories exist.
No, when you add them, then there are all these light states, the twisted. So I guess you will have a lot of. I mean, it's not just the pure Chern-Simons, but then there will be all the twisted states also. But in any case, maybe
No, but that would be Chern-Simons coupled to a vector theory,
Yeah.
which will not have the number of bulk fields will be that of Vasiliev theory,
Yeah.
and then there will be some boundary degrees of freedom, roughly. On the other hand, you could have adjoint theories which have a much larger. So there it sounds like there are two consistent theories. The first one of which is just the pure Vasiliev theory, and the second one has this enormous amount of matter. Here you're saying that the first one does not make sense. That's right, maybe I haven't.
Yeah, the vector theories, I don't think they make sense on the sphere. And I think that's sort of uniform in the sense that I don't think there's a consistent quantum bulk theory. At least there might be one as a string theory, but not as a pure Vasiliev theory.
But suppose we just take the vector model on a torus. That has additional states, but no additional bulk fields, right? Because the bulk fields are in one-to-one correspondence with the operators, with the states on S2. So it's not like you're going to, the bulk dual of that will have additional bulk fields.
Yeah.
Will just have Vasiliev.
Right, but right.
On the other hand, if you take the adjoint theory, then you've got zillions of other bulk fields. So in that context, it's true you need some boundary degrees of freedom to get the Chern-Simons thing, but it still seems like a distinction to me.
Yeah, there is, in fact, there's no analog of that in the.
Yeah, so here you say that there would. Okay, yeah, it looks different. Looks like in high dimensions you should have a consistent theory with Vasiliev's bulk fields plus some other boundary stuff, and Vasiliev's bulk field plus a lot of other bulk fields. When you say 2 dimensions, it's...
Yeah, the first one, I'm still not sure what it means. What is the consistent bulk description of?
Because you have to formulate that boundary stuff.
Yeah, and there's a continuum of them. And
there's a continuum of them.
Yeah. So it may be some... yeah.
It would be sort of like the question of the algebra of single trace operators on a torus in Chern-Simons matter theories. Like, as long as that makes sense, there will be some.
Yeah, so there's as a field theory, it's a perfectly well-defined field theory. So there should be a. So it's like in this 2D CFTs also. The 2D CFTs are perfectly well-defined CFTs, and it may be that it's the large N limit which is maybe a little singular or something because of this continuum. This thing. Of course, in the higher dimensional case, the difference is that on the sphere it's perfectly fine.
And the sphere is important because it gives you the
states, the mapping to the bulk
fields.
Yeah.
Yeah. So it's not a continuum of bulk fields; it's a continuum of something else.
Okay. Yeah.
Okay, just one more question.